Welcome everyone to the webinar. Thanks for joining us. My name is Matthew Gilbert. I'm joined today by my University of Sheffield colleague Linwei and Catherine Rankine and Vincenzo Reale from Arup. This is the running order for today's webinar. What you'll see is at the end of the series of presentations, there's a Q&A. So if you have any questions during the course of the webinar, just use the question box in GoToWebinar and we'll pick these up at the end. Before we get into the webinar proper, I just want to say a few words about ICAD, who are bringing you the webinar today, the Integrated Civil and Infrastructure Research Centre. And I've picked out a few snippets from the vision statement and mission statement from ICAD that are relevant to today's session. So resource efficiency and introducing new technologies capable of delivering step change, in this case in the design of structures using optimization. Also say a few words about Peregrine. That is why we're here. What is Peregrine? It's a layout optimization plugin for Rhino and Grasshopper. It's designed to allow structurally efficient concepts to be rapidly identified. Prototype version was developed as part of a UK government-funded research project. If you want to find out more details about that, there's a website, buildup.org, that you can look at. And the current version has been developed as part of a follow-on project involving the University of Sheffield, Arup, and Limit State. And the Peregrine plugin is now maintained and developed by Limit State, and you can download a copy from the Food for Rhino website if you haven't already. Okay, just again, before we get onto the webinar today, just give you a heads up on some future events that are going to be happening in the next few weeks and in September. So the first of these is a webinar this time next week, where we'll be looking at some of the more advanced aspects of Peregrine, advanced features. So today's webinar, we're really going to scratch the surface. So if you like what you see and you want to find out more, then please join us for next week's webinar. In 2 weeks, we'll be holding a hands-on workshop, an online workshop, and hopefully you'll be able to follow along with the various examples that we'll be presenting, and also get one-to-one assistance if needed, using the online platform that we'll be using then. And then in early September, we've got a final workshop where we'll be looking at the more advanced features of Peregrine, and also hopefully using a recent released version of the software which has additional functionality. So if you're interested in any of those, go to the BuildOpt website and a registration link so you can sign up for any of those events. All of them are free of charge. Okay, so I'm going to kick off the webinar now with just an introduction, a brief introduction to layout optimization. What do we mean by layout optimization, and how can we take advantage of it? So, a bit of history. More than 100 years ago now, Australian engineer called Mitchell showed that orthogonal layouts of elements give rise to mathematically minimum volume truss structures. This is actually an extract from his paper. It's quite difficult to see, but we've got a central load, downward load at C. We've got potential supports at A and B. And you can see this arrangement of orthogonal tension and compression members providing the structure, the least volume structure for this particular problem. In the case of Mitchell's paper, clearly it was a time before computers were around, so all the calculations were analytical and quite involved, and it didn't really catch on for another 50 or so years until the advent of computers. But a big question you might be asking is how important is layout? I've got a really simple example here. It could be the simplest possible example. just to illustrate how important layout is. So we've got a vertical wall and we've got a point load to support some distance away from that wall. And we've got 3 possible structures to carry that load. The first one, and we've got the tension and compression members arranged orthogonally, which as we've seen, Mitchell identified as being most optimal, giving rise to the least weight structure. In this case, we can see that the volume of material required for the middle structure is significantly higher, 50% higher, but the volume for the right-hand structure is significantly higher, so it's more than twice as high. So clearly, even with this very, very simple structure, we have quite significant benefits from having the layout on the left, where we've got these orthogonal members. And for more complex problems, we can find larger reductions in volume still, or increases in volume if you have the wrong structure. Now you might say, we don't often see structures with these very acute angles. Actually, I beg to differ. You can see structures with these very acute angles, which are not particularly structurally efficient, very readily. Here we've got an electricity pylon where we've got exactly that scenario. So I mentioned that we can now, with the advent of computers, identify layouts automatically. It's actually been available since the 1960s, a technique called numerical layout optimization, or the ground structure method, devised by some American mathematicians. The idea is that if you have a point load, support, and an unknown area where the structure can inhabit, first thing you do is you populate that area, that design domain, with nodes. You interconnect those nodes with potential truss bars in this case, and then you use optimization to find a minimum volume subset of members, giving rise to the optimum structure. And the benefits of this formulation are many. One is that the optimization formulation, the basic optimization formulation proposed in the 60s at least, is linear, so we can get a globally optimal structure, and we can do that now very, very rapidly. Secondly, when we're treating the sort of low volume fractions that we typically are when we're designing buildings, bridges, and so forth, this approach, this discrete layout optimization approach, is much more suitable than continuum topology optimization approaches, which you may have seen. Continuum topology optimization approaches are very useful for component design and mechanical engineering, for example, but they're less useful when you have a structure which is inhabiting a very small proportion of the final structure. Sorry, a small proportion of the original design domain. If you're interested in this area in terms of the details of the formulation, how we can solve it, and how we can solve it in the most efficient way possible, I just refer you to a recent paper which has a Python script which will allow you to solve this kind of problem very readily. Now, one of the problems with layout optimization, one of the things that stopped it being used for many years, is that it can give rise to quite complex structures. Because we have got this grid of nodes, we can end up with quite a large number of those nodes actually being used, and we end up with these messy structures. So here's a 3-dimensional example. It's actually another example from Mitchell's 1904 paper. It's called a Mitchell sphere. So the idea is that we have a torque on the problem, either side of the design domain, and we're trying to find the minimum volume solution. What we can do is we can actually, as a post-processing step, we can start with the layout optimization solution, and then we can add the XYZ coordinates of the nodes as design variables. And that allows us to simplify the structure, but it also allows us to reduce the volume of the structure. So we get a double benefit, really. We get a benefit of the structure being simpler, but also more optimal. And so that's a very valuable tool. And again, there's a paper describing that at the bottom of the slide. However, even with that enhancement, we might find that the structures are impractical in the sense that they've got too many members, too many joints, and so there are various techniques available to simplify the structure. And the approach that we use in Peregrine is to basically solve the original layout optimization problem, or layout and geometry optimization problem, if we want the rationalization, and then agree or specify a trade-off and say, actually, I'm happy for the final structures to be 5% heavier than the original one, but I want to minimize the number of members, for example. In which case, in this case, you would move from the quite complex structure at the bottom of the screen to the structure at the top of the screen. And then we've got also intermediate structures as you can see. And the way we do this is actually by having sort of existence variables for each member, and we rather than having them as 0-1 variables, which makes the problem more computationally expensive, we have a smooth representation, and that allows us to get solutions quite rapidly. And there's a paper there for those of you who are interested in this particular area of study. There's also actually a very recent paper that applies mixed interlinear programming, so that actually does have 0-1 binary variables that's been published in the last few months. And for those of you who are interested in optimal structures, as well as Peregrine, I just want to draw your attention to a new web app which has recently been launched. So you navigate to layout.com, and you can either read in some of the pre-built examples, or you can actually create your own problems. And you get these characteristic structures where you've got orthogonal tension and compression members. And you can also use the simplification techniques, which I mentioned, to identify simpler variants of these structures. And because it's on the web, you can use it on a desktop, laptop, or also on a tablet or even a mobile if you want. So lots of fun, very quick and easy to find out what the optimal structure might be for any given design problem. Okay, so that's just a sort of a quick introduction to layout optimization. I'm going to transfer over to my colleague, Linwei, who's going to take you through the next part of the presentation.
Okay, hello everyone, I'm Linwei. So I'm the main developer of the Peregrine plugin, and also the main researcher of all the methods behind the thing. So I'm glad I can show something about the Peregrine plugin to you. So in order to create and solve the optimization problem, we actually developed a range of Grasshopper components. And the workflow in Peregrine has 3 parts. So the first part is quite simple. We basically define the problem, and then we use layout optimization to find the optimal layout of the structure. And then we use some post-processing techniques to improve the practicality of the designs. So to define the problem, we need to specify a couple of things. So first is the design domain. Currently, we can have 2D and 3D geometries, and also you can put the geometries together, then the structures in each geometry will be optimized simultaneously, and sometimes you can come up with some very interesting designs. And for the loading type, we have some of the common loading types like the point, line, and surface load. And for the line and surface load, they can also be made transmissible, which means the loading locations can also be optimized with a structural form. And for the support types, we have the point and surface support. And also we have the directional support, which can become very handy in some special scenarios. So once we have all the okay, so once we have all the problem definition defined, then we can use it in the optimization algorithm. And the first stage is the layout optimization, as Matthew mentioned. And this algorithm is very robust and it's very efficient. So if we use more nodes in the optimization, we can get better and better solutions. And as you can see from the curve, it will approach to the analytical solution. However, if we look at the early part of this curve, you can notice that the error percentage drops very quickly to below 1%. And at this point, we notice that the CPU cost is just 1 second. That means we can use the layout optimization in two ways. So the first is to use layout optimization to explore the problem settings very rapidly. For example, we can very quickly change the design domains, load and support types, and see the outcome very rapidly or almost instantly. And another usage is to basically get the benchmark for some practical designs. Once we have the it's not moving. Yeah. So once we solve the layout optimization problem, as Matthew mentioned, the solution might be impractical. So we need to rationalize the solution using the rationalization tool. And the rationalization basically performs the geometry observation. So it moves the node to more optimal locations to further improve the structural efficiency. Also in this step, it will try to rationalize the layout by looking at some of the common practical issues, such as the closed nodes will be merged. Now also crossover points will be created, and also the inline and collinear members will be removed. And after the rationalization, the structure is normally simpler, and also it has a better form to indicate the load path. However, it's not necessarily practical. So that comes our another tool, which is the simplification tool. As Martin mentioned, this is based on the smooth heaviside projection. And currently we have 3 types. So the first type is to reduce the number of members, and also we can simplify the joints, which is to reduce the number of members connected at each joint. And also in some scenarios, we would like to simplify the most complicated joint. So once we have all the solutions, will be useful for us to basically gather all the solutions and compare them. And also it's really handy that we have a benchmark solution, which is obtained, as I mentioned earlier, by solving a standard layout optimization with more nodes. As we can see, that's one very complicated structure behind. And this is used as our benchmark. Then you can use this solution to compare all the alternative designs. So you can see the simplified structure is only 3.5% heavier than the benchmark. And because this time we know the benchmark, so we get confidence that although the structure is simplified and is not that bad, so we can basically have confidence to select this design as a prototype for some future modifications. So I would like to use a short video to show how the Peregrine works in Rhino and Grasshopper. So for those of you who are not very familiar with Rhino and Grasshopper, this is a parametric tool, and you can basically create and modify your geometries using some controls. So once you have all the geometries created, then you can link these geometries to the Peregrine components, such as the design domain, support, and load conditions. And then all this data will be collected and in the solver, and we can now perform the layout and geometry optimization. So now the video is recorded in real time, and want to use a very simple example to show how efficient this plugin is. So you can very quickly change the location of the loads, and you can almost instantly see the result. And this will provide some very interesting interactive tool at early conceptual design stage. So you can basically change the loading type and change the support type and inspect the load path and understand the structural behavior very rapidly. So, and our previous project finishes in 2019, and our current project also finishes. However, we do have some research outcome haven't been actually implemented in the previous versions of Peregrine, and we do have something in development. For example, we have the local stability considered in the layout optimization. So we're likely to get some branch-like structures which are good for bipolar buckling. And also we have the linear global stability in the optimization. So the structure will be globally stable. And also we introduce the grillage optimization, which will identify the optimal arrangement of beams under pressure load. So when this is combined with the truss layout optimization, this will allow us to perform some holistic building design optimization. So we can simultaneously optimize the floor plans and the bracing members in a building structure. That's everything.
Thanks, Linwei. So we're going to hand over now to Catherine, and Vincenzo is going to provide industry perspective to application of layout optimization using Peregrine.
Hi, everybody. So we'd just like to share a bit about our experiences in industry as we've gone through the process of sort of supporting the research and development of this plugin, and gone from sort of the initial research and conceptual use to starting to apply this on real world projects. So sorry, there's three areas that we've mainly focused on our involvement within this project. First of all is to change the sort of conceptual thinking of engineers to learn from these things that obviously people like Michel and Maxwell developed by hand without any kind of computers back in the day, but nowadays we think it's really important to reinforce among all of our engineers. We also have applied the plugin to optimize some sort of routine structural forms that are fairly common, and we've also done some concept generation and form finding for more advanced structures. So first off, we'd like to just very quickly run through. Some of these might look quite familiar to others who have heard about layout optimization before or seen the Michel truss examples, but this is just a collection of sketches that were done either by students or by engineers at Arup in response to a very simple problem with a centrally loaded truss. And you can see that sort of the intuitive engineering forms might be applying some traditional structures, but the question here is about the absolute minimum volume, and it's sort of understanding that the solution to absolute minimum volume is this Michel truss, a half bike wheel, and we then can layer on top of that the real world engineering constraints that that enable something to be buildable. And as the trusses get more and more complex, these differences in weight become more and more apparent. So in this example where the domain is restricted, you can see that the theoretical solution is significantly lighter than a traditional truss like a Pratt truss. And once you get to a more unusual problem like this, those decreases become a lot more marked. So we have a lot to learn from these types of structures. Our main involvement in this research has really been in the third image on the right-hand side here. So taking the analytical solutions that were developed 100 years ago and the numerical solutions that were initially developed in the 60s and are being further developed by the teams at Sheffield and other areas. Arup's main interest and focus has been on the practicality and simplification to try and link this into real projects. So a couple of examples of how we've done that might be a simple multi-story transfer truss, for example, where we've got a tall building with a loading bay that we needed to transfer out a significantly loaded column over the top of that. So previously we had explored various options for trusses or plate girders and made some initial allowances. And by using the Peregrine plugin, we can develop a simple truss form that is then benchmarked against an analytical solution. In another case study, we've applied this to an office floor structure with precast planks sitting on trussed secondary beams. And there was an architectural aspiration for a very, very light and open full headroom in this project. And so we explored the different options for tubular trusses and what kind of simple reference designs or more complex designs we could apply that would identify opportunities to make this as optimal as possible and meeting the architectural goals. The other thing that's really useful to learn from this is, as you might have seen in some of the sketch examples, the most simplified direction that this goes in is to get you a Warren truss that's at the bottom there. And it's really useful to sort of follow this process and understand the benchmarks that lay behind why we've got to that solution as being the most efficient for this case. And here it's applied on the project. And this is a further option that the contractor obviously wasn't in a position to build this complex trusses with the connections designs that are available nowadays, but we think with the advent of things like 3D printing in metal and so on, we could start seeing structures that look like this in buildings. And finally, here's a truss that is hidden from view, so it doesn't have architectural constraints, and we were purely driving the structural design of this, supporting a stone stair in an existing building where we had complex boundary conditions that meant we needed to limit the amount of load that we were passing to the structure. So if we apply some initial constraints, we see that this forms a sort of arching action, but this relies on a very large horizontal reaction at the top. So if we don't allow it to have this horizontal reaction at this point, we then get a more appropriate truss solution, which is still lighter than the initial design. And that's just to highlight the concern, the importance of understanding the boundary conditions. So I'm just going to pass over to my colleague Vincenzo, who's going to talk about the more esoteric applications of this.
Thank you, Catherine. So now I'm going to present a series of more speculative case studies where we try to apply the plugin in order to, first of all, study the applicability on different typologies, exploring alternative structural option, but also propose solution that could be the basis of a discussion that we would have with the architects. So although these are very early studies, we think that there's quite some potential that can be envisaged in these. The first one I'm going to show you is art gallery building for a competition. So basically the brief was to design a structure spanning up to 32 meters, and the architects were really keen to both reduce the material consumption and exploring a structure which was actually exposed and visible. So basically we just took the competition brief as a layout, and then we started applying the plugin on this brief basically. And then we went through a series of iteration trying to rationalize it and reduce the number of members, for example. And even if we didn't get to a solution that it's optimal for many various and different reasons, the architect was really keen on experimenting, and basically it gave us some ideas on how to develop this further. So I mean, you can see that you can use this tool basically to generate a structure that is completely exposed, and it has also some static characteristic that you don't have necessarily to hide within the rest of the structure. Similarly, we try to apply the same process to the competition for a DOM structure. And at the beginning, what we were doing was generating a fixed domain and then applying the plugin within this fixed domain. We were getting at the beginning this very complex structure with multiple elements. But if you start then refining the number of elements, what's we think is very interesting is that some pieces of the structure start exhibiting some very interesting smaller components, smaller parts, which can be developed as a system on their own. So again, you can run Peregrine on a fixed domain and then get some areas of your building that give you a structural idea to develop further and proliferate throughout the project. And then because Peregrine is embedded in Grasshopper, what we found very interesting and powerful is also to run some parametric studies. So not having a fixed domain, but being able to change the boundary condition, change the application of the point loads in an interactive way. So starting from a very simple configuration with just a limited number of support to a more complex one when we proliferate the number of support. And because it's parametric, the load per each one of these members is reduced. Therefore, you actually get viable arrays of different solutions that, again, even if they are not optimal and biddable as they come out from the plugin directly, you can use as a starting point for a conversation with the architect. And actually, I mean, some of these are actually buildable as we see them, which is, we think, very, very interesting and very, very powerful. So here you can see some of the array tables that we produced for this competition. And similarly to this process, we use the same process on definition of a freeform stadium. Again, the domain here was defined by the architect. There was an architectural constraint, but then we subdivided this domain, this outer boundary of the structure, into different segments and parametrically controlling these different segments, therefore giving rise to different structures, which at first might seem very complex, but again, because we have the power to refine them, to change the constraint, and to look into them, we can then see emerging within the overall structure some interesting patterns, some interesting ideas that can be developed as a viable project solution. And then to conclude, we wanted to show you one of our early tests with Peregrine. The idea for this project was a cantilever structure at the top of the tower. Basically, we needed a structure to support an overhang. So again, the process was the following: defining structural boundary, structural domain for the structural supports, and then run the plugin. And I mean, at this time, we tried to run it without any sort of post-processing to see where the maximum optimization of the structure will push the structure, also which kind of aesthetic quality would emerge from the utilization of the plugin. And again, we're not saying this is currently viable with the current tool that we have at the moment in terms of complexity, but at the same time it gives us a glimpse to where structure can be pushed if we were actually able to exploit these techniques to the most. That's all for me.
Thanks very much, Vincenzo. That's fantastic. So now there's an opportunity to have a look at the questions that have been asked. And if you haven't asked any questions yet, please feel free to add those. I'm just looking now at the question pane. Just give me a second while I expand it. So is the meeting going to be shared later? Yes, hopefully we'll record it and we'll make this the recording available. Does the plugin also support multiple load cases? Very good question. We didn't have a chance to cover that, but yes, it does. So one thing that you'll find is that an optimal structure under a single load case ends up comprising of orthogonal tension and compression members. When we have multiple load cases, that quality may not be present. So you end up with slightly different configurations, and actually Warren truss, for example, becomes very efficient when you have lots of load cases in some cases. Where can I find information on the optimization formulation of the plugin? If you look at in the manual, there is some information, but also some references. The next question: can we apply these techniques to regular building structures? I think Linwei he mentioned that we were going to be developing or making available a version hopefully in September, which will allow you to have a holistic optimization of a building structure. I mean, some of the outcomes from the work we've done in that area so far have been quite very interesting. So we've had very large reductions in amount of material potentially, which is clearly of significant importance given the climate crisis. Mention about 3D printing, metal 3D printing structures. Is it possible to add ad hoc material properties in the plugin? It's possible to include representative properties of whatever material you're working with. In relation to 3D printing, that's something that's certainly been explored actively, both in a research sense, but also starting to move into prototype structures. Certainly at the University of Sheffield, we're involved in a project where we have large 3D printed trusses or joints being fabricated. Does the plugin allow for verification of vibration in floors, footfall analysis? The answer is no. It's possible to link up the output from the plugin to other tools, analysis tools, and you could do vibration analysis in that case. We're also looking at formulations which do take into account frequency constraints in the formulation, and those may become available in a future version. Probably really good to see so many questions, but they're coming thick and fast. I'm not sure if we're going to have a chance to answer them all, but let's see how we get on. Can you control the complexity of the initial outcomes instead of having to post-process the outcome every time? Well, in a sense, in Grasshopper, if you link together a number of components, then you can directly obtain a simplified outcome. You don't need to concern yourself with an intermediate unsimplified outcome. So I guess the answer is yes. You don't need to manually do that. You can have that as part of an automated workflow. This is probably a question for Catherine or Vincenzo. Christian from Bureau Happold: what's the reaction from steel fabricators when they see an unconventional truss? And secondly, is the domain limited to 2D or 3D? from Arup's presentation, I assume it can be 3D. So yeah, absolutely 3D. For some of the concepts, it's easier to get those across in 2D. So that's why a lot of our slides show 2D examples, but certainly 3D. But if you want to reply, Vincenzo, perhaps to the question about steel fabricators of Catherine.
I can reply.
Okay, sorry, go ahead.
Yeah, we actually, they were quite interested. We had some discussion at the ICAD headquarters in London, and there were a couple of people from contractors, and actually, because I mean they want as well to push their industry further, they were quite keen in understanding how this technique can be applied to their domain. So, of course, if you were possibly to present this straight away in a project without having a previous discussion with the contractor, I imagine that it would be difficult unless you use it for simpler project, as some of the one we showed you. It doesn't necessarily mean it's a completely different bespoke approach to structural engineering. But if you want to move to structure which are not very common at the moment, I think you would find that some of the contractors are actually keen to get on board, because I mean, for them, if they manage to overcome the issues in the production, utilizing less material or like improving the performance of the structure that they provide is a good for the industry as well.
Yeah, I'd just like to echo that with a couple of examples. So one of the two-dimensional examples that I showed was a truss underneath a stair, and the contractor and cost consultant basically said that they would view those as equal at a sort of stage, maybe stage 3 or stage 4 level of costing. And once you actually get into construction, the number of connections and the number of the piece count was kept the same, because we used the simplification constraints to keep those the same. So in that situation, it was viewed as equal. In the other situation where we used the sort of secondary beams trusses, that was presented at a much earlier stage in the process, and at that point, when the contractor was just starting to come on board, their advice was that the move and the difference between plate girders versus tubular trusses far kind of overshadowed the difference between different types of tubular trusses. And apart from the main issue that we actually found was that when you had a complex tubular truss, in order to be efficient, you needed to have very, very small, thin-walled sections, which were very difficult to weld. So that was actually the practical constraint on making something sort of very spidery structure. I hope that helps.
Thanks. There's a related question. Any completed project on this research? I think your colleague Will had a project that was going on site. I'm not sure if I ever did get completed. I think it was an oil. I can't remember exactly what the project was. Do you remember, Catherine?
It was a screen. I think it was a screen shielding some equipment. And I think that one's gone to site. And the media hub with the trusses used as secondary beam supporting precast planks, that's on site now.
Okay, good. Just a couple more questions, and then we'll have to finish because of the time. Some some of the if I don't get around to answering your questions, I will send some email replies. Some of them look a little bit in depth to cover here. So there's an observation which I think is I think it follows on from Vincenzo's presentation. Interesting aesthetic qualities that arise from the process, and it could allow engineers, but not just engineers, but also architects, to be inspired by the structures that we see from the tools. Would you agree with that, Vincenzo?
Yeah, I mean, as even Catherine was showing at the beginning, we think that the use of this tool, even the online, the web interface that you showed at the beginning, I think they're very good tools for educating to how structures works. And I was actually discussing with an architect the other day, and I showed him the web interface, and it was for them interesting and fun just to see what by changing the constraint you can get a different structure, and start thinking, oh well, then this is how we could build around the structure. So yes, I think it's a tool for architects and engineers, and it helps understanding how structure ultimately works.
Okay, thank you. The very last question, just a very quick one. Can we limit the solution to compression-only elements? You can change the material properties so you end up with compression-only structures. And the related question about whether it deals with linear material properties. In a sense, it's plastic material properties. So for multiple load cases, you'll assume plasticity. So whether that's linear or non-linear, it depends on your viewpoint. Well, thanks everyone. Thanks to all the speakers for contributing to the webinar today. So Linwei, Vincenzo, and Catherine, and thanks to everyone who joined for the session. As I mentioned, hopefully there'll be an email coming through in a few days with a video that you can share freely with colleagues. So with that, we'll finish the webinar. Many thanks, everybody, and goodbye.
Thank you.